So for the three-phase diagram, we're typically looking at a graph of temperature versus energy. Taking a look at if you add energy or remove energy, how does the temperature change? And for a typical substance, like let's say you just got maybe a block of, let's say a block of ice. Let's assume that the ice starts off very cold. So it's got very little energy and very low temperature. So if you take this very cold ice, and let's say you add some energy to it, what would you expect to happen to a block of very cold ice if you add energy to it?
It would start melting.
It might start melting eventually, but yeah, I would expect it to warm up first. If it's, I mean, if you start adding energy and it's already at a certain temperature, it'll start to melt. But if it's too cold, adding energy will just make it warm up. So if you add energy, the object is going to get warmer. Which means which direction would we go on the graph? If we're adding energy and the object is getting warmer, what's that going to look like on the graph?
It's going to go up.
Yeah, it's going to go up because we're increasing the temperature.
Yeah.
And yeah, also to the right because we're adding energy. So yes, that would be a positive slope. And it turns out that that ends up being a straight line because there's a certain ratio of how much energy you add versus how much the temperature changes. And that's consistent throughout the process. You add energy, temperature goes up. Add the same amount of energy more, and you get the same increase in temperature, up until you reach a certain point. And for ice, that's specifically going to be at 0 degrees Celsius. At 0 degrees Celsius, adding energy doesn't make it warm up anymore. Instead, once it reaches 0 degrees and you add more energy, what's going to happen? Right, it's going to melt. It's going to go through this phase change. At the melting point, which we usually write as T sub melt. For H2O, that's 0 degrees Celsius or 273 Kelvin. For other substances, it'll be different temperatures, of course. But once it reaches the melting point, we add energy and we get a phase change. The ice is going to change what phase it's in, from solid to liquid. But as it does so, it doesn't change temperature. While the ice is in the process of melting, it stays at 0 degrees until it's finished melting. So what would that look like on the graph? If it's staying at 0 degrees, but we're adding energy, which direction are we going?
To the right.
Yeah, we're going to the right. There's no up or down motion at all because the temperature is not changing. Moving up or down on this graph means you're changing the temperature, but that's not happening during this process. We're only adding energy, we're keeping the temperature the same. So this horizontal line represents the phase change process. The melting process, or in reverse, you could say if it's liquid, you could remove energy to make it freeze, make it solidify. So you could go either direction on this, depending on whether you're adding energy to make it melt or removing energy to make it freeze. And where you are on this bar basically represents how much of your substance is solid versus liquid. At this corner, that's all solid. A little bit to the right, you've melted a little bit of it, but it's still mostly solid. Halfway across, you're now half liquid and half solid. All the way across, this is now representing all liquid. So the width of this bar represents how much energy you'd have to add to melt the whole thing. Or alternatively, how much energy you have to remove to freeze the whole thing. Once you get to that final point, the far right point on this bar, it's now all liquid. And if it's all liquid now and you add more energy, what's going to happen? If you just got this puddle of liquid water, yeah, the liquid is going to heat up, which means we're going to have another diagonal. Now we have a liquid, so we had solid, warming up, and then the melting process. And now if you add more energy, the new liquid water is going to warm up. So again, we're going to go up and to the right. That'll have a constant slope. It doesn't have to be the same slope as the solid line, because liquid and solid of the same substance can have different properties. It turns out that the liquid line and solid line will usually be the same or pretty close to the same slope, but they don't always have to be. So the liquid is going to warm up as we add energy, getting hotter and hotter and hotter until what temperature for water? What's the hottest liquid water can get?
100 degrees Celsius.
Yeah, once we get to 100 degrees Celsius, something else happens. Because 100 degrees Celsius is the boiling point. So at that point, we continue to add energy, and instead of the water heating up, what happens instead? Yeah, it's going to evaporate. We get another phase change. So at this point, we're going to have another horizontal representing that phase change, the evaporation, because we're adding energy to break the bonds, to allow the molecules to leave each other's presence. But that adding energy doesn't cause any change in temperature. We've got hot liquid water at 100 degrees Celsius. Add some energy. It's now mostly liquid, but partly a gas. Some of it has turned to steam. Then we add some more energy. Now it's maybe half liquid, half gas. We add some more energy. Maybe at this point, it's now completely a gas. It's all boiled away. So at this point, it would be now entirely a gas. We've got a cloud of steam at 100 degrees Celsius. And if we were just boiling this in an open pot, the steam would presumably just drift away and be no longer really something we care about. But if it's in an enclosed container, if you trap that steam and keep adding energy, once it's completely steam, if you still add more energy, what's going to happen to the steam? If you take the container of hot gas, yeah, it's going to get even hotter. Add more energy. We now have, let me label this, we got liquid, evaporation or boiling. And then at that point, we now have a gas. We're adding more energy, so it's going to get even hotter. So we add energy, increase the temperature, add energy, increase the temperature. This will also be a constant slope, but it doesn't have to be the same slope as solid or liquid, because again, the different phases can have different properties. Gas, liquid, and solid, even of the same substance, can react to heat in different ways. The same overall pattern, but different rates of how much energy versus how much temperature change. And since it's a gas, if you keep adding more energy, it's just going to get hotter and hotter. There isn't really another phase change beyond that. If you raise the temperature to absurdly high amounts, you get situations where the individual molecules can shatter and the electrons get knocked off of the molecules or knocked off of the atoms. But that's way beyond the temperatures we're going to be dealing with in this class. So we can essentially say this just keeps going as high as we care about. Likewise, in the other direction, if you remove energy from the solid, it's going to keep getting colder and colder and colder, approaching no energy and no temperature. But that's colder than we really care about anyway. So this is what we usually call the three-phase diagram, in the sense that it's got these three phases, solid, liquid, and gas, and also the transitions between them. And we can use this to keep track of what's going on with these substances, what happens when we add energy or remove energy at different temperatures. Sublimation, yeah, you can also represent sublimation on a graph like this. It doesn't really end up being a three-phase diagram exactly, but you can still use the same sort of graph. Because what does sublimation mean? Like, for instance, if you've got, let's say, dry ice. If you take dry ice, solid carbon dioxide, and add energy to warm it up to a certain point, yeah, it just transitions directly to a gas. So for dry ice, you've got a solid phase. And then when you hit a certain temperature, the sublimation point, temperature of sublimation, you reach that point, And at this point, you get a phase change. So that's going to be another horizontal. You add energy and you're not changing the temperature, you're just changing the phase, allowing molecules to split apart from each other. Going from all solid, not to liquid, but to gas. Some of the solid just turns directly into a gas, then more of it turns into a gas and more of it turns into a gas until eventually you get to a point where it's all gas. And at that point, you continue adding more energy and the gas is now going to get hotter and keep going. So it really turns into more of a two-phase diagram. And the usual terminology used for that is if you are going from solid to gas directly, that's called sublimation. Whereas if you are removing energy, causing the gas to turn directly into a solid, that's usually called deposition or deposition, in the sense that the gas molecules are depositing onto a surface and becoming solid directly. So this happens with certain substances at certain ranges of pressure. For instance, carbon dioxide at standard pressure will turn directly into a solid instead of going through a liquid phase. If you change the pressure, you can get carbon dioxide to have a liquid phase. So it really depends on what the pressure is. But at standard atmospheric pressure, carbon dioxide and certain other substances only have a two-phase diagram. Still the same basic pattern, you're just basically skipping the liquid phase. In fact, if you adjust the pressure, adjusting the pressure changes the melting and boiling points. So if you can get the melting and boiling points to get closer and closer together, they eventually merge together and you just have a sublimation phase or sublimation process. You're skipping the liquid phase entirely. Any other questions on that so far?
So for the corners, for graphs like sublimation, is it still a phase change?
This horizontal bar represents the phase change, yeah. The corners basically represent 100% one phase or 100% the other phase. So for instance, this corner here represents entirely solid. This corner represents entirely gas. If you're at a point like halfway between, like exactly halfway between, then that would mean half of the substance is solid and half of it is gas. And that's measured by mass, not by volume. Whereas if you're, let's say, a third of the way, you're closer to the solid phase. So that means 2/3 of it is solid and 1/3 of it has turned to a gas.
Okay, and that's true for the three-phase diagram too, right? Like,
yeah,
I think, yeah, okay, thank you.
Yeah, exactly. So for instance, at this point, exactly halfway between these corners, this would mean that the substance is half gas and half liquid as measured by mass. Or at this point, it would be like 2/3 solid, 1/3 liquid. And it really does just turn into what percentage of the way along this bar are you, because the amount of energy required is really a per kilogram thing. Like if you add a certain amount of energy, you've melted a certain number of grams of the substance. Add the same amount of energy again, and you melt the same number of grams again. So it's a constant amount of grams per joule of energy added, or grams melted per joule of energy added. Any other questions on these graphs so far? And one of the main uses of a model like this, other than just getting a general conceptual idea of what's going on, is being able to tell what type of energy is changing. If you're just adding energy to this substance, we want to consider what kind of energy is being increased or decreased. And that really depends on what kind of change is happening. If you're talking about, for instance, let me make this a little longer. Let's say you're going through a phase change. Let's say you have liquid water that's already at 100 degrees. And let's say you want to boil, not the whole thing, let's say you only want to boil 2/3 of it. So maybe you start with 9 kilograms of water, liquid water, and you boil it so there's only 3 kilograms left. 2/3 of it has evaporated. In that case, this procedure is a certain amount of energy added. This amount of energy would be the delta energy, change in energy. And if we're talking about a phase change, what kind of energy are we really talking about there? How would we categorize this change in energy?
Thermal? Or
What was that?
was it thermal energy?
Thermal has
wait,
more to
no,
do with the
it's
temperature
constant.
change.
Yeah,
Yeah, if we're talking about a phase change, we generally call this bond energy. And the reason for this is at the microscopic level, if you're boiling the water, what's happening with individual molecules? What's happening to those molecules? Yeah, the bonds are breaking. In the liquid phase, you start with the molecules fairly closely bonded together. They're able to move around, but they can't really leave each other's presence. They're stuck close together. Breaking bond, going through the phase changes involves breaking bonds. You're adding energy to make the molecules get further apart. You're breaking the bonds that connect the molecules together. So they're no longer connected. They can move around freely, and it's now a gas, or at least partly a gas. So bond energy is the type of energy of the substance that's changing when you go through a phase change. Either adding energy to break bonds, making the molecules get further apart, or removing energy to allow bonds to form. And this can seem kind of counterintuitive because you have to add energy to remove bonds and remove energy to allow bonds to form. Ultimately, the reason for this is that bonds have a negative amount of energy. One bond has a negative amount of energy. And we're going to get into the details of why this is later on. But if a single bond has a negative amount of energy, you'd have to add energy to cancel out that negative and get rid of the bond, or remove energy from the substance to create that negative and allow a bond to form. So if it helps you remember which direction is positive and which direction is negative, each bond has a negative amount of energy. So you got to add energy to break the bonds and remove energy to allow those bonds to form. And again, we're going to get into a lot more detail on the microscopic side of things later. But for now, you can just say bond energy is the kind of energy that's changing when these substances going through a phase change. And note that there's no temperature change during that process. In a standard phase change, the temperature should remain constant. There are some exceptions to this we'll get into later. But in a typical situation, if you have an object that's at its phase change point already, and you're changing its phase, you're not changing the temperature at the same time. Any questions on that so far? Alternatively, if you're looking at a temperature change, like let's say you start off with cold solid and you warm it up. So you're going from a cold solid to a warmer solid. In that case, you're starting with this much energy and you're ending with this much energy. So this would be the change in energy. But what do we call that type of energy if it's associated with a temperature change? Yeah, this is what we would call thermal energy, delta E thermal, usually just abbreviated as delta E sub TH. So that's a change in thermal energy. Any object has thermal energy, and its thermal energy changes if the temperature changes. Likewise, any substance could have bond energy, but the bond energy changes only when the phase is changing. And we don't really usually care about how much energy the object has. Typically, what we care about is how much is the energy changing, because the changes are really the important part we're looking at. What's happening to the object, not just what it is, but what's happening to it. So thermal energy changes if the temperature is changing, increasing or decreasing. Bond energy changes if you're breaking or forming bonds, going through a phase change. And typically on a graph like this, if you're going to the right, that's an increase in energy. If you're going to the left, that's a decrease in energy. So a graph like this can also make it a lot easier to figure out, are these deltas positive or negative? If energy is increasing, then delta E is positive. If energy is decreasing, then delta E is negative. Any questions on that so far? So let's investigate some of the mathematical details here, starting with bond energy. If you wanted to figure out how much energy it takes to melt something, like let's say you've got a block of ice and you're melting it. What properties of that block of ice do you think are going to make a difference in terms of how much energy it takes to melt it? That is, what about that ice determines how difficult it is to melt the whole thing? Yeah, the mass is going to be the main thing there. For instance, if you have 2 blocks of ice, let's say a 1 kilogram block of ice and a 20 kilogram block of ice. Let's assume they're both already at the melting point. Which one is going to be more difficult to melt? That is, which one's going to take more energy to melt? Yeah, the more massive it is, the more energy it's going to take. And specifically, how do you think those delta E's are related? If you want to melt this whole thing and also melt this whole thing, how much more energy would it take, would you expect? Yeah, it should be 20 times as much. Melting a 20 kilogram block of ice is equivalent to melting 20 1 kilogram blocks of ice. So it should take 20 times as much energy. Excuse me. And generally, we can say these are proportional. The delta energy bond, that is how much energy it takes to melt that object, should be proportional to, and we usually write this as delta M in the sense of how much mass is changing phase, the change of the amount of mass. And of course, the 1 kilogram of ice becomes 1 kilogram of liquid water. So there's no change in the total amount of H2O that we're dealing with, but we are changing how much of it is solid versus how much of it is liquid. So that's what the delta M signifies here, a change in how much mass is in each phase. Have you seen this proportionality symbol before? If we say that delta E bond is proportional to delta M, what does it mean if 2 quantities are proportional to each other?
Is it like they follow the equation y equals?
Sorry, y equals what?
Like kx, where k is a constant?
Yeah, in general, if we say that y is proportional to x, in the sense that, for instance, multiplying y by 5 also means multiplying x by 5. They get multiplied or divided by the same values. That means that y can be written as some constant times x. Might be 5 times x, or might be 3.5 times x, or might even be a negative 3.7 times x or something. But proportionality always means you can write it as one of the values equals some constant times the other value. We might not know what that constant is, but we can usually find it experimentally. Take some measurements on values of x, take some measurements on the corresponding values of y, plug those in, and you can solve for that unknown constant. So in general, anytime you know 2 quantities are proportional to each other, or even just suspect from experiments and experience that they should be proportional, you can always write that as one of those values equals the other value times some constant. So that's really the key to a lot of what we're going to be doing here. If you know that 2 quantities are proportional, you can write one of them is equal to the other one times some constant. And in this case, that constant has different names in different textbooks, I think largely depending on whether you're looking at it from a chemistry background or a physics background or an engineering background. This constant is sometimes called the latent heat of the substance, or the heat of melting, if you're talking about this transition, or heat of boiling, if you're talking about the other transition. Or sometimes called the enthalpy of melting or boiling. Or sublimation. You could have, for instance, heat of melting or enthalpy of melting, or heat of sublimation, enthalpy of sublimation. These are all just different terms for the same thing. In some textbooks, that's written as a capital L for latent heat. In the Physics 7 series, it's usually written as delta H. It's written as delta H, but don't worry about this delta. This delta doesn't really mean H is something that's changing. Delta H is just the symbol we use for the enthalpy of melting. This constant that you multiply by how much mass is changing phase to figure out how much energy it costs to make that happen. And I think it is often very useful to think of this as a cost or as a difficulty level. Lots of delta E means it costs a lot to melt that object. Any questions on the terminology there so far? So we've just introduced a new quantity, this idea of latent heat or heat of melting, enthalpy of melting, whatever you want to call it. Anytime you introduce a new quantity, especially something like a constant in proportionality like we just did here, there are a few very useful ways to investigate what exactly that means. One way is to look at the units of measurement. For example, if we consider mass, what units of measurement do we usually use to measure mass of an object? Yeah, mass is typically going to be measured in kilograms. And what units do we usually use for energy? Yeah, joules or sometimes kilojoules. Which means in order for these to match up, what units does delta H have to be measured in order for this to even work? What fraction would have to go here to make these sides equal to each other? Yeah, that's going to have to be joules per kilogram. That way, kilograms and kilograms cancel out, and you're left with joules, which is the units we want for energy. Or alternatively, that might be written in kilojoules, and then we'd have kilojoules per kilogram. It doesn't really matter whether it's joules per kilogram or kilojoules per kilogram or joules per gram, as long as you're consistent about it. The important thing is that the units should match up throughout the problem. So delta H is typically going to be measured in kilojoules per kilogram. That gives us some information. It tells us what we're actually measuring in terms of the units. And also another very useful way of exploring what a new quantity means, think algebraically here. If you're dealing with some mysterious variable, how do you usually find more information about that variable in terms of algebra tools? What's the usual process in algebra for finding out more information about a mysterious variable in an equation? Yeah, we can isolate it. And in this case, all we need to do to isolate delta H is do what? Yeah, if we just divide both sides by delta M, we get delta energy, specifically delta E bond, divided by delta M. So this is a very useful way of thinking about what delta H means. Delta H, the enthalpy of melting or latent heat, whatever you want to call it, is this ratio of how much energy you're adding or removing, divided by how much mass changes phase as a result. So for instance, if you have some substance and you add, let's say 500 joules to melt 2 kilograms, then you could just plug those in and divide 500 joules divided by 250 kilograms, sorry, 2 kilograms, and you get delta H is 250 joules per kilogram. So that's what delta H is describing. Delta H describes the ratio of how much energy per kilogram. In fact, you can even read it like this. 250 joules per kilogram means it takes 250 joules of energy to melt each kilogram of the substance. So it's very useful in cases like this to think of this as a unit rate of change. Delta E over delta M means how much energy it costs per unit of mass, how much energy per kilogram it costs to melt that. Or you could even think of it as a sort of a standardized measurement. Delta E bond is how much energy you're adding to melt some substance, some object. Delta H is the energy it costs to melt exactly 1 kilogram. So delta H is just delta E bond standardized to exactly 1 unit, 1 kilogram of the substance. Any other questions on that so far? And what do you think determines the value of delta H? Yes, specifically when we're talking about a phase change. If we're talking about something like a temperature change, then that's delta E thermal instead of delta E bond. So that would involve a different formula. But in general, anytime you're talking about a phase change, you can use the idea that delta E bond equals delta mass, how much of the mass changes phase, times this constant of delta H. But what is it that determines delta H? Like if you've just got two objects that are both the same mass, let's say both 5 kilograms, are any two 5 kilogram objects going to cost the same amount of energy to melt? Or what else could be different about those objects? Yeah, the type of substance. Specific heat is more to do with temperature, but it's another property of the substance that we're going to look into later as well. But in general, this delta H depends on what type of substance we're dealing with. For example, if you have 5 kilograms of ice that you want to melt, and also 5 kilograms of iron that you want to melt, those are going to cost very different amounts of energy. So delta H is a property of the material the object is made of. Property of the material. And since it's a property of the material, you can look that up on a data table. And of course, you could measure it in a laboratory setting. If you've got tools that you can use to measure how much energy you're adding, and you've got a scale so you can measure how much mass is changing phase, you can measure those in an experiment, divide, and calculate delta H for the substance. But of course, we're not the first people in history to try melting ice and measuring the results. So instead of calculating it every single time, you can look up delta H on a data table. And that's typically going to look something like, let me pull this up. This sort of thing here. You can just look up, for instance, if you want to melt a kilogram of ice, you can look up ice. And notice that we've got, for H2O, we've got a variety of different values. What we care about, though, is the heat of melting. So heat of melting, and note that there's two different values here, 333.5 and 6.01. What's the difference between those? Why is this listing two different values? Do you notice any difference in how these are presented? Yeah, kilograms versus moles. Because I said earlier, we can think of this as kilojoules per kilogram, how much energy it takes per unit of mass. But it can also be measured as kilojoules per mole, how much energy it takes per mole of the substance. You can describe how much of something there is as number of kilograms or number of moles. So which one of these you use just depends on how you're measuring the substance. If you're measuring the mass of the substance in kilograms or grams, you'd use this one. If you're measuring the substance in terms of how many moles of it there are, then you'd use the 6.01 instead. So either of these work, they're both equivalent, but the important thing is to use the one that matches up with the units you're already using. So for instance, let's say we're talking about, let's say we want to melt 5 kilograms of ice. Which one of these would we use? Yeah, the one on the left. 333.5 kilojoules per kilogram. So if you wanted to melt 5 kilograms of ice, we could say delta E bond equals delta M times delta H. If you're melting 5 kilograms, delta E or delta M would be 5 kilograms. And then delta H would be the listed value, 333.5 kilojoules per kilogram. And then you could multiply those, and that'll tell you how much energy it costs to melt the 5 kilograms of ice. Kilograms cancel out, so the result will be measured in kilojoules. Any questions on that so far? And over here in the next cell, it also lists another value in kilojoules per kilogram. When would you use that one instead? Or how would you decide which one of these to use? Why does it give these two very different values for heat of melting? Yeah, heat of melting is 333.5 kilojoules per kilogram. Heat of vaporization is 2,257 kilojoules per kilogram. So yeah, you choose which one based on what type of phase change you're dealing with. So most of these substances have two different values, one for melting, one for vaporization. And those also work in reverse. If you're freezing the substance, going from liquid to solid, you'd still use the same 333.5 as you do for melting. If you're condensing a substance from gas to liquid, you'd still use the heat of vaporization. So these aren't really about direction, they're just about which pair of phases we're talking about. Likewise, for carbon dioxide, as we saw earlier, there's only one phase change from solid directly to gas, the sublimation. So carbon dioxide would just have a single value, heat of sublimation. And of course, that could be listed in kilograms or in moles. Any questions on that data table so far? And by the way, in terms of just the amount of these, like 333.5 versus 2,257, the heat of vaporization is a much larger value. What does that suggest? What does it mean if the heat of vaporization is much larger than the heat of melting? Yeah, it takes, in this case, a lot more energy to vaporize than it does to melt. And note that this is ignoring the amount of energy it takes to bring it up to the right temperature. If you just have ice that's already at the melting point and you want to melt it, it takes a certain amount of energy. If you've got liquid water that's already at the boiling point and you want to vaporize it, that takes a lot more energy. And ultimately, this is because going from solid to liquid, you're breaking some of the bonds, allowing them a little bit more freedom to move. Going from liquid to gas, you're breaking all the rest of the bonds, allowing molecules to move far apart from each other. So typically going from liquid to gas is going to take a lot more energy than going from solid to liquid, just because you're breaking so many more bonds. And this seems to show up in all these other substances as well. Gold has a much higher heat of vaporization than heat of melting. Lead, small heat of melting, large heat of vaporization. This seems to be a pretty consistent pattern because you're breaking some of the bonds versus breaking all the rest of the bonds. So a table like this can be really useful. Anytime you want to figure out how much energy it takes to melt or boil something, you can look up the delta H appropriate for that substance and that phase change in the data table, and then multiply that by the delta, the amount of mass that's changing phase, the delta mass in that situation. Any questions on that so far? Then let's try out a quick example here. Let's say we have liquid water and we want to freeze it. Since it's liquid and turning to solid, we don't really need the gas phase, so I'm going to clear up some space here. Let's say we have, start with, let's say 10 kilograms of liquid water that's already at 0 degrees. And let's say we want to freeze, not necessarily all of it. Let's say we just want to freeze half of it. Or not half of it. Let's say we want to freeze 2 kilograms of it, resulting in 8 kilograms of liquid, 2 kilograms of solid. And we want to know how much energy transfer that's going to take. We can start by taking a look at that on the three-phase diagram. Let me tighten this up a little bit. And I often find it useful to draw out the whole diagram as sort of a dotted line or drawn really lightly. And then fill in more detail on what part we actually care about. According to this description, on this graph, where do we start out? Yeah, we're on this second diagonal because we know it's liquid. And specifically where on this second diagonal? Yeah, at this bottom left corner. Because we know it's 0 degrees Celsius, so that's the coldest the liquid can get. And then where are we going? Are we going to the left or to the right here? Yeah, we're going to the left because we're freezing it. If we're freezing it, do we have to add or remove energy? Yeah, we got to remove energy to allow those bonds to form. And also just conceptually, if you've got water and you want to freeze it, you got to remove energy from it, extract heat. So we're going to go to the left, but not all the way. We're only going to freeze 2 kilograms of it. So are we going to end up closer to the initial point or closer to this far corner? Yeah, closer to the initial. Because we're only freezing 1/5 of it. So we're only going to go 1/5 of the way towards that far point. And it's a good idea to draw an arrowhead somewhere on that line just to show which direction this transition is happening. So that's the entire three-phase diagram that we care about. We only care about this portion because the rest of it isn't happening. And examining that portion of the energy bar, this is the delta E bond we care about here. And to organize the information here, it's often a good idea to draw what's called a energy interaction diagram. We got the three-phase diagram to figure out what types of energy are changing. The energy interaction diagram describes that type or types of energy, usually drawn as sort of bubbles. We've got bond energy, and in this situation, would you say the bond energy is increasing or decreasing? Is this gaining or losing energy? We actually wouldn't need values on the graph. We have enough information right here to figure this out. Because we know how much we start with, how much we end with, and we can also look up the delta H of water in the data table. So if the graph was marked with values, we could just compare how much energy do we start with, how much energy do we end with. But we have enough information in the description here to figure that out separately. But if you do have a very clearly labeled graph, you can get the energy values from the graph as well. In this case, though, since we're going to the left, that seems to be a decrease in bond energy. So I'm going to draw a little down arrow here. And also, we usually list what's called the indicator. And the indicator is a measurable quantity that you can see changing that tells us that type of energy is changing. So what's changing here that tells you that bond energy is what's important? Yeah, we're going through a phase change. However, we can't really just list phase as the indicator here because phase doesn't really have a numerical value. We want the indicator to have a numerical quantity that we can plug into the equation. So the indicator we typically use for bond energy is mass. And specifically, we've got 2 masses here. We've got mass of the liquid and mass of the solid. Generally, for this situation, you want to use mass of the higher energy state. Would you say that liquid or solid is higher energy? Yeah, liquid is higher energy than solid. So I would say mass of the liquid here. As you go through this process, as you're freezing it, do you end up with more or less liquid than you started with? Yeah, we end up with less. In fact, we can even list out the initial amount of liquid and the final amount of liquid. We started with 10 kilograms of liquid. We end with only 8 kilograms of liquid. And of course, we still have conservation of mass. There's still 10 kilograms of H2O. It's just that some of it has changed phase. So we end with less liquid than we started with. So we'd say mass of the liquid has decreased. And note that these arrows match up. We can say the bond energy is decreasing because the amount of liquid is decreasing. And if this is the only type of energy we care about, if we're treating bond energy of the ice as our entire system, would you say this is an open system or a closed system? Does this liquid have to interact with something else? Yeah, it's an open system. And we usually draw that by surrounding it with a dotted line instead of a solid line. So this dotted line surrounding it means this is an open system. Because to make this happen, you've got to remove energy from it. So typically we would draw this as an arrow leaving the system labeled heat, which we usually abbreviate as Q. Heat represents the transfer of energy. So heat is leaving the system to allow this to freeze. And now that we've got this energy interaction diagram, we can turn that into an equation. And typically the equation is going to be conservation of energy. In general, the total change in energy of the system, if it was a closed system, no interaction with anything outside, that would be delta E total equals 0. But since this is an open system, we do have a change in energy. And in general, that's going to equal heat plus work, heat being the transfer of energy due to temperature differences, work being a mechanical transfer of energy. We'll look into work later, but for now, we can say this is just a transfer of energy that's called heat. So delta E total equals the heat transfer. And what's the only type of energy changing here? Yeah, so delta E total is usually going to be several delta E whatever's added together, but in this case, it's just delta E bond. We can then fill in the formula we saw earlier. Delta E bond is the same as delta M times delta H. For delta M, how do you calculate delta anything if you have the initial and final values? Yeah, delta M is just final mass of the liquid minus initial mass of the liquid. So 8 kilograms minus 10 kilograms. And then delta H, we can look up on the data table. That's the 333.5 we saw earlier. Eight minus 10 is going to be how much? Yeah, so -2 times 333.5 will be negative 667 kilograms canceled out, so we just get kilojoules. So the amount of heat required to make this happen is negative 667 kilojoules. And what do you suppose the negative signifies here? What does it mean for heat to be a negative number? Yeah, heat is being removed from the system. A positive or negative on heat, and also for work, represents which direction the transfer is occurring. If heat or work is leaving the system, then that's going to be treated as a negative value. Whereas if heat or work is entering the system, that would be treated as a positive value. And the important thing in terms of the delta M is that using mass of the higher energy state, liquid in this case, means the correct positive or negative sign will automatically show up when you subtract final minus initial. And you should do a quick reality check at the end to make sure it makes sense that this is negative because heat is leaving the system. But in general, as long as you're careful to always use mass of the higher energy state, subtracting final minus initial will automatically give you the correct sign. Any other questions on bond energy? All right, then we will take a look into thermal energy and some more examples of that next time. In the meanwhile, feel free to contact me by email or on Discord if you want to request any topics for next time, or if you have any other questions, and I will see you then. You're welcome.